Great, thank you. So I'll just share briefly some of the things that what we are doing in our company. We do quite a bit of custom development, and one of the recent developments was dealing with Internet of Things systems, particularly in healthcare, and then the next set of clients would like to do that in automotive space. So I would like to share with you some of the typical things that we have when we work with systems like that. So I'll scribble a couple of things on my tablet here. So one of our applications in healthcare is involving having patients.
Vladimir. Try that.
Okay, you hear me? All right. So we have a patient. So we have a patients that usually don't feel too well. And instead of having them go to see the doctor, we actually put various sensors on them. And then we monitor various parameters like temperature and pressure. And now we will be getting also some new sensors that can capture the heart rate and similar. And then what is happening with these sensors, we are using low energy Bluetooth, and we are sending this to their mobile device. And then this mobile device is going to send this through the internet into our systems in the cloud. And this is now where the interesting part actually begins. And there we have first systems that are dealing with ingestion of data. And then when we ingest the data, we are going to do some processing. And also we store this data into data store. This is usually some data store that will support time series data. It can be Apache Cassandra, which we use in a number of projects, or OpenTSDB, which is based on HBase. Now, when we do this, there are two interesting flows that are happening from here. One is the batch analytics. And that one is interesting because we have these patients who are involved in clinical trials, and then we aggregate the data, and then after a fairly long period of time, we evaluate the effectiveness of these different drugs that these people are getting. And this is then producing interesting reports that can be analyzed. But there is usually no great rush in order to accomplish those. One of the other areas is that we would like to be able to notify nurses and physicians when something interesting is happening with our patients. And this is where we have a very different need. This is where we would like to have nurses who can go and attend to the patient when something is happening. And the interesting thing here is that this area is fairly real-time oriented. So here we have a real-time, and here in this other branch we have the conventional batch processing. Now, when we started working with our clients, these older systems were typically based on plain Hadoop, and later we have been looking into Spark to improve our efficiency. But the problem in this space is that sometimes we would like to react much faster than the Spark is allowing us. And we were looking to introduce some true streaming systems in this picture. We have been looking into various solutions out there. And a solution that we have found in Flink captured our attention because it enables us to combine both the batch processing and the real time in the same framework. And also, many of these analytics that we are doing are going to be using very similar code. So using the Kappa architecture, so having a combination of Lambda architecture with the very similar code for both batch and streaming is something that was very attractive to us. Now, our systems in the current version are not really designed to respond to something like heart failure, where you need to intervene within a really short amount of time. But we have clients that are trying to do something really similar, but they are operating in automotive space. So you have cars that are instrumented with various sensors, and they are sending these values there. And also, one of the interesting things in automotive space is that the data that we are dealing with are not coming only from the cars, but they're also coming from environment. So there is another aspect of this system, and this is the data integration in real time. So we would like to be able to achieve the integration of not only other cards, but also with other systems. And that was the motivation for looking into applications that are better support the streaming and batch processing. So when we look into development of these applications, so first we have seen traditional approaches that went from warehousing, then we have seen batch, and then we have seen the growing popularity of streaming systems. And these streaming systems were coming with different APIs, with different runtime characteristics, and we have seen that there is really a space for something new. So one of the things that is interesting for us is the set of capabilities that we are getting with streaming. So one of the things that was really interesting in the beginning is that we could combine data from different sources and merge them and have this fusion of data. And we have seen something like that in real-time systems with sensor data fusion and similar. The second thing that was really interesting for us was the development of low latency applications. In my company, one of the things that we were doing are the real-time systems that are used in oil industry, and responding often within milliseconds is a very, very important thing. And now with the Internet of Things, we've seen that pretty much everything can be instrumented and can be sending us signals. And having a really low latency below the second is something that we would like to see. And we see that in many cases, the streaming capabilities are more powerful than things that we can achieve just with the plain batch. And you see, looking into what is happening in the world of data systems, we could see that there is quite a bit of interest in development of such systems. And we have been following one project that is coming from European research, the project Stratosphere. What is interesting for me is that this project is not starting exploration of big data space from scratch, like what we have seen with Hadoop. But having the background from Technical University of Berlin, this is the team that was famous a long time ago for their work on parallel database systems and optimization of relational database systems. So one of the things that was really exciting for me is that the knowledge that we have accumulated in the development of conventional system is not forgotten. It does not need to be reinvented, but we can actually build on top of that. And this project started from certain premises, how to build a new data engine. And one thing that was visible is to start with streaming, and then support for optimization. So when you are having bad jobs, we would like to be able to optimize them based on the data sources, based on the nature of our development. Are we running on a local machine? Are we running on a small cluster, large cluster? What is the distribution of data? All of these things we would like to have considered for optimization. The third aspect is that when you look into machine learning algorithms, you would like to be iterating. And this is something that traditional big data systems were not doing very well. And finally, there is a need in graph processing to maintain a mutable state, and various algorithms will be updating this state. So what was the desire in this project is to have an engine that would natively support these use cases and not start from batch and then let's see how we can tweak the batch to support these other cases. So when we say the native support, we are not thinking about running conventional MapReduce jobs a number of times. But we would like to have iterations as the normal part of the development, as a really low-level construct that is built into the system. The other thing that is not ideal is if you take your stream of data and start shredding it into pieces, and they say, well, these are the small batches of data, and if I process them fast enough, it would look like a real streaming system. And there are differences between discretized streams and true streaming systems. So when you are working on true real-time systems, you would like to be able to process events as they come without being forced to batch them. The project eventually resulted in what is today known as Apache Flink, and it has a couple of interesting areas. So probably the most interesting part in this space is going to be the core of the system, which is the distributed streaming data flow engine. The interesting thing here is that the streaming is the native mode of operation of the system. And you can view the batch as a stream that will terminate at some point. One of the other things is that a system is very flexible when it comes to deployment. For the development, we prefer to run it in a local mode, and that goes through clusters and cloud applications. One of the things that this picture does not show is that the system is quite agnostic when it comes to data sources and sinks. So you can connect to a variety of systems, from distributed file systems to many of the databases out there. On top of this runtime, we have the two APIs. So in the past, everybody was starting from batch processing and dataset API, which also includes, on top of it, some machine learning libraries, graph libraries, and things that we have seen in other systems. But what is really interesting is this data stream API, true stream processing, very elegant API. So if you look into the API, you will see that it looks very, very similar to Scala collections, to which you apply different operators. And there is exciting work on adding the table interface on top of that. And also, what is particularly interesting for me is complex event processing. We are going to talk a little bit about this today. Now, in the big data community, there is one interesting project that is happening right now. This is Apache Beam, which is based on Google Dataflow. And Apache Flink is the most complete runner for this API today. So this is quite interesting. Apache Beam will provide a uniform interface across a variety of big data systems. So when we look into a typical application architecture for a system like with Flink, typically we see that we have a variety of data sources. Then we have a log system that is ingesting the data. We do the analysis with Flink, and then we can store the result into various systems, including a variety of database systems. Conventionally, many of the applications would get the results from Flink, put it in a database, and then we would query this data in these databases. One of the things that is coming later is ability to actually query the Flink itself, so you don't need to put the data necessarily in the store to achieve that. So typical architecture. And looking into some of the key characteristics of Flink in this space is first the orientation of the engine to execute everything as streams. Pipeline execution, we are going to see in a moment what is that. And also, one of the very attractive capabilities is that you have the back pressure from the source all the way to the sink. One thing that is of interest is the optimization. So in comparison with various other systems, Flink is trying to do a lot of optimization on its own. And this is something that we have used to have in relational databases. When you have your database, there is an optimizer that will calculate the access path. It will consider a variety of factors and then choose the optimal path of execution for you. Data flows that can be iterative, state that you can mutate and save. And one of the things that Flink introduced very early was the managed memory. So the objects are stored outside of the JVM heap. There is a separate part of the system that is enabling you to fill up the memory of your servers, and you're not impacted by the limitation of the JVM memory management, the garbage collection. And when you know exactly what is your access pattern of data, what is the expected life cycle, then the managed memory can introduce significant optimization, both in speed and ability to store more things. So one thing that is very interesting is when you start from a Flink program, you are going to have a pre-flight part of the execution that is running on client that is going to do basically the compilation and optimization. What you get as a result of that is the data flow graph. And you can think of it that this graph is the logical graph that can be then optimized and adapted to your actual platform. So the system can choose the right path of execution. And then eventually you will deploy that on your cluster that consists of master and the workers. So this ability to optimize things is, for me, quite interesting because we don't need to spend too much time fine-tuning and optimizing the system on our own. So we said that the streaming architecture is the heart of the system. So how do you build a streaming architecture? So you have a couple of things that you need to accomplish. First, you have the basics, and this is the pipelining, moving and processing of events through the system. You can also replay the streams when needed. On top of that, you would like to be able to manage the state. Also, you would like to be able to have a backup and restore, support the fault tolerance. And then you would like to have a nice APIs. So the APIs that we have in Flink are, interestingly enough, coming in several flavors. You have Scala API, which is my preference. But there is also Java API, because not the whole world will move to Scala really soon. And also, eventually, we have support for large deployments with high availability and scale in and scale out. One of the next things that is coming is automatic dynamic configuration of systems, so you can dynamically expand when you have the need. So pipelining is the internal mechanism that is used for processing of events. So this is happening in the distributed fashion. You have the events that are moving through the system. And conceptually, events are moving individually. In practice, you typically have groups of these elements that are moved together in order to improve the throughput. And this is something that we have seen in parallel databases some time ago. We have the state for each of the operators that is doing the processing. And these transformations are going to match to steps like map, reduce, and so on. One of the really interesting capabilities is working with streams of data that fit into certain windows. And we are going to see in a moment what they are. Now, looking into the state of these operators, there is a new feature where you can take out the state and move it to the external system. And the current version of Flink is using the RocksDB. RocksDB is an embedded database developed at Facebook, very high performance, and a very good choice for preserving the state. Now, event-based systems are having the notion of windows. And the typical form of windows, to draw you a little picture here. So when we look into the windows, we have the simplest type of window. Let's say you have a data stream that is coming like this. And then you have various events. The tumbling windows are the windows where you have no overlap. So you have one window like this, and then the next window is like this, and so on. Then you have the windows that are sliding windows. So have your event stream. These are going to be the windows where we have a certain overlap. So you have one window that looks like this. Then the second window is going to be like this. The third window is going to be like this. And then there is going to be some amount of processing that will be happening over events that you have already seen. But one of the really exciting forms, and this is what other systems don't have, is the notion of events that are based on time, when these events actually happen. And when you look into these events, so if you peek inside, you are going to see that event like this are going to have some payload, which represent your data. But also, there will be the information about the time. And what is really fascinating about this notion here is that this is the time where things happened in the application. This is not the processing time that you see right now on the server. And this is really exciting because for many applications, just imagine distributed applications or information that you're getting from mobile devices. You can get disconnected for some period of time. And there is a notion of the time where the event actually happened. This is what you would like to preserve. And this is you would like to reason about. So this notion of time is extremely important for the time-based windows, which are a unique feature of a Flink. So talking about time, we have mentioned processing time, ingestion time, and particularly interesting for us, it is the event time. You can write your extractor that can get this information from the events that are happening. Now, when you're dealing with such advanced mechanism, you would like to have ability to fine-tune and to define the grouping of the events, because certain events belong together, and they can be a result of a session that user may have. Now, if you look into other streaming systems, how do you identify that things belong together? Now, usually you would say, well, I'm going to have the window, and then every 5 seconds I'm going to treat these events as if they belong together. But this is not the case if you have sessions. For example, if you have a session of the user who is interacting with the website, there is some notion where you know, OK, we are starting the session. You have some period of browsing, and maybe later we are going to finalize the purchase. When we are done with that, this is the end of the session. And it can take a different time to actually complete. So the watermarking is the mechanism that can be used to fine-tune the processing. Talking about iterations, you have a conventional type of iterations, and that is you will use the whole input that is available at this time, and data is basically reprocessed. And this is typically the first step that you would do. But then you quickly desire to optimize these things. And in Spark, for example, we have to write our function that would operate in such incremental fashion. In Flink, we have the delta iterate, runs only on data that has changed. And that is very convenient because it gives us significant speed up, because we typically process just a fraction of these events. Fault tolerance for the systems. They have been various semantics among these systems. One that was promoted for a long time as acceptable is at least once. It turns out that this is not good enough, and we would prefer to have exactly once semantics for the events. And we would like that this exactly once happens from end to end. And this is something that Flink supports out of the box. There is a variation of Chandy-Lamport algorithm that is allowing to achieve this. So exactly once is a very convenient feature for applications. As we are working on the fault tolerance, checkpoints is a mechanism that enables us to save the state. So if something breaks during the processing, we can rewind to the logical time of the last checkpoint and then continue from there. One of the new things that we see in Flink is a notion of save points. And these are the checkpoints that have been taken by the user. So they are available externally. They will be stored in a data store, and they don't expire. And you can even explicitly trigger them and then use them. So you can issue a command, Flink save point, and then the ID for your save point. And you could even resume the execution of your system by saying Flink run. Then you put the path to your save point, and then the application jar file that would run the system. And you can imagine this is a great feature for production, because it enables us to better handle the updates, updates of both of our application and updates of Flink, migration from one implementation to the other. And we could even run various what-if simulations. You start from one save point, and then you try to run some different execution. So somebody recently commented that this behaves almost like a GitHub for the state of the streaming system. You can build a graph of these transitions. So very excited about this new feature. So when we look into the whole set of benefits, we see a couple of things. The processing that is happening in the streaming engine does not block. And that results in much higher throughput and lower latencies for processing than in some other systems. I have some references for you later where I point to a couple of benchmarks that can be done at Yahoo, at a couple of other organizations. And there is one that is particularly interesting, benchmark from Korea, which is showing how Flink can execute things in parallel. And this is thanks to the non-blocking nature of execution. Then we have the business logic is separate from the recovery. So we have that the checkpointing interval is the configuration parameter. When you do this checkpointing in Spark, you know you have to really write code in order to achieve that. And it is a non-trivial code. So we get it fairly automatically. And one thing that we particularly like is support for fairly rich window semantics. So particularly the notion of session windows is very practical. The notion of event time is fairly unique in this space. And one of the things that is quite interesting, Google Dataflow has a very rich set of features for processing streams. And Flink is currently the most complete implementation of this algorithm. And there is a great alignment between the Beam project and what Flink is offering when it comes to windowing semantics. A couple of other things. True streaming latency, so we can process things that are happening within milliseconds, exactly one semantics, and low overhead for recovery are very attractive points. So looking into code, the code that we see here is a Scala code. Scala is my preferred choice when it comes to implementing big data systems. Starting from scalding that was invented at Twitter, which was the DSL for Scala that would compile Scala operations on collections to the operations on piped architecture from cascading. We have also seen similar things in Spark. And if you know the Spark API, you will immediately recognize similarity because the inspiration is the same. The Scala collections are so powerful, and Scala provides for very convenient development of domain-specific languages, so it is a natural choice. I like those APIs because they are less verbose than Java APIs, but Flink also has Java APIs for everything, so it may be easier to introduce in more traditional organizations. So here we have an example that is defining the data that we will be processing. There is a class word. So when you introduce something like this, it is going to define a set of objects that consist of the word and the frequency. We have first example of the dataset API, which is the batch API. And in the API like this, you would read some input, and then you would do your fairly normal operation that you would do in a Scala program. So you're going to take the lines, which is the dataset of string. We are going to execute flat map. Flat map is going to do two things. The first thing it is going to do, it is going to split the line using the space. And then it is going to do the map from each of the word to an instance of the word class where we have the word as a string, and then we have number 1. You can imagine that the input is coming in lines. So if you would do just plain map, you would have the collection of collections that contain word. Flat part will execute flatten operator on this, and we end up with collection of words that is going through the system. Then we do the grouping by word, and then we sum this and get the frequency. The streaming API is very similar. You can notice that there is a little difference here. Instead of reading the text file, we are going to get the input from some socket. The code that is actually doing the processing looks the same. You see the lines are the same. And there is one line that is different. And when you are working with stream, you need to think of what is the window. And this is this line here. We are defining here what is the window and what is the sliding parameter. And this is something that is very attractive. Pretty much the same code that can be used both for batch processing and for the streaming systems. So very attractive thing. One thing that is, let me make it a little bit bigger. So here is the variation of this program. It is still a batch program that is going to take the inputs from the stream. One of the nice things here is that when you are developing with Flink, you can very easily work in your development environment. There is a local mode for execution. You don't even need to install Flink on your machine. It is enough to define dependencies for your Maven file, and you will be able to run this. And you don't need to run any special runner. You can just go to the code that contains main and say run. And I have now my program running. So Flink is now running. And in this version, I'm going to open my monitor, terminal. And I will zoom in a second so you can see what I'm doing. So I started the netcat command. So I'm going to stream something on port 9999. And I'm just going to enter. So just make sure that my program is running here. All right, and now I hit enter, and you can see here at the bottom we have the result. So what I want to say here is not to impress you with the API, but I want you to see how convenient it is to develop with Flink. So you're not wasting much time on trying to get these things to run. All right. So batch on streaming is Flink's interpretation of batch execution, which is mapping the batch processing to streaming. And now I would like to talk to you just a little bit about the complex event processing, which is a new feature in Flink. And I'm particularly excited about this thing because when I was writing my PhD, I was implementing complex event processing in C++. And I was using Antler and defining my own language. And now I have this thing in Flink, and it even works on a big scale. So when you're defining complex event processing systems, you have a certain set of operations that you want to perform. So you want to be able to define the beginning state. So you will start matching events. The events can come in different order. These events need to satisfy different conditions and need to be of certain type. So there is the next event. So you can say, after this event, I'm going to see the next event. There will be no other events in between. I can also choose to say followed by. That means this event will come at some point, not necessarily immediately. I can filter the event by the where condition. I can define some time interval. So I can say, if this happens within this time range, I'm going to respond. And also, I can define what is the type of the event. So there is a subtype parameter. And here is a little example. So this is the implementation that is simulating things that would happen in intensive care units. We are monitoring the patients. So we have the warning pattern, which is 2 high heart rate events with a high blood pressure within 10 seconds. You see, so this is the pattern that we want to match. And currently, CEP for Flink supports only Java. But you can see it is fairly intuitive. So you can define there is the alarm pattern, and then you would say we are beginning with the measurement, and we are checking that the type of the event is the heart measurement, where the event get risk is greater than equal than 1. There is a little formula that would calculate that based on the blood pressure and heart rate, followed by, so there will be another event, we call it middle. It is a blood pressure measurement where the risk is greater than or equal to, followed by, so the third event is coming at some point, and it is also heart measurement where the risk is greater than 3 within time seconds. So this is very powerful, very, very natural way of expressing the rules that we have in a problem domain in our system. Everybody wants to compare a Flink with Spark and Storm, so I could not disappoint you. So I have a couple of slides here that I have borrowed from data artisans. The interesting thing about Flink, it is a true streaming architecture, and I would particularly like to point here that we have a low latency as opposed to Spark, which is using micro-batching that operates as a medium latency system. So you have the link there. You can go and see a little bit further. There are some other comparisons. And when I'm thinking about comparing different systems, recently Apache Beam emerged as a framework that provides a very nice model for classification and comparison of features of different systems. So the Beam is coming with a very comprehensive model for semantics of different big data, and particularly streaming applications. And it is organized along dimensions. So what results are we calculating, where in the event time, when in the processing time, and how do these different refinements relate. So when you follow the link, you will be able to see the comparisons of the Beam model itself, cloud data flow implementation from Google. There is the Flink, and there is Spark. And you can see the different capabilities of these systems. You can see Flink is satisfying more of these options than many of these other systems. So quite interesting. So follow the link. It is also good to learn what are other powerful capabilities that you expect to see in streaming. Couple of benchmarks. I'm not showing these benchmarks to start some war about how the tests are not done properly. Usually when you show the benchmarks, I just want you to see that it is something that is worth investigating, something that is worth looking for, and that the advantages when it comes to performance can be quite significant. So here is one from Strata San Jose. Quite interesting measurement, 50 million events per second. When you get rid of Kafka, that was slowing down the input. And here is some other benchmark that is comparing the latency. You can see Flink and Storm are operating with the low latency, while Spark is not performing so well. So a couple of things that are coming. SQL for streaming. This is also a quite interesting feature, very productive feature. Apache Calcite is the SQL layer that allows independence from a SQL in different stores. Dynamic streaming, as I mentioned. Ability to query the state of the system, so you don't need to offload the stuff in the database. And a couple of other things like Mesos support and over-the-wire encryption for the systems. So quite active community. A couple of indications about the growth, and I just picked up this last night, 1,300 stars and 800 forks. So there is a growing community. And at the end, I collected 2 pages of good resources, so you have an easy start. Naturally, first, the Flink resources. If you're interested in performance comparisons, quite recent reports. If you are new to streaming, there are 2 really good articles on the O'Reilly site, Streaming 101 and 102. Also, that will include various newer features that we see in Apache Beam. Also, nice explanation of watermarks. And Beam itself provides a nice framework for comparison. And finally, Slim Baltaji has a nice set of links on various big data systems and particular emphasis on Flink. So that was all. Thank you very much. If you have questions, just hang around. I'll be here. Thank you.